We are presenting our work, Contextual Fact Ranking and its Applications in Table Synthesis and Compression. This is a joint work between Google Research and University of Illinois Urbana-Champaign. Nowadays, modern search engines increasingly incorporate tabular content as part of the query result. However, there is a lack of content for tail queries, hence the ability to automatically synthesize tables to expand coverage is desirable. One of the main sources for these synthesized tables is Wikipedia, such as named lists on the category page. A collection of entities of such name list can be added to the synthesized table, and facts are retrieved from their respective Wikipedia info boxes. For example, from the Wikipedia category page, Open World Video Games, a synthesized table can be constructed for all such games, leading to a carousel as depicted in the slide. Naturally, the ability to rank facts according to their informativeness to the query context is crucial to the quality of the synthesized table. In addition, even when a table exists to support a table answer, it is often not suitable for presentation as is due to limited space on devices, and needs to be compressed. For example, given the query, future tallest buildings, Google used to show the table, as shown in the slide, which is generated by projecting the first 4 columns of the original table. Most users, however, would prefer to see facts such as height, floors, or year of completion, which are more informative to context terms, future, and tallest. This also motivates our problem of ranking facts based on the context. Next, we formally introduce the problem of contextual fact ranking. That is, given some entities in a context of succinct natural language description, which we called title, identify the most informative facts for the entities collectively within the context. As shown in the example, there are 3 facts, height, floors, and year of completion, that are identified as most informative with respect to the title, future tallest buildings. We propose to employ supervised learning to rank the facts. As a first attempt, we consider the ranking problem as binary classification. That is, classifying whether a fact is informative or not, based on the context and the associated entities. Our dual encoder architecture is built on top of a sequence model, aiming to develop an appropriate representation that carries semantics for the context in each fact, inferring only from their respective word sequences, but learning across lots of training examples. An alternative approach is to frame the ranking task as pairwise classification, that is, classifying the relative ordering of 2 facts by their informativeness in relation to the title. We use Siamese network to learn an informative scoring function. As shown in the slide, a Siamese network consists of 2 identical base neural networks, with the same architectures and weights. Each base model is the same as what we have described in the previous slide, mapping title-fact pair to a ranking score. As a result, although we train a Siamese network on examples consisting of pairs of facts, we can just use one base model for inference at serving time, as shown in the right-hand side of the slide. One of our work's main contribution is how we collected the training data. Since deep learning is typically data-hungry, we propose to collect training labels automatically at scale from the open web. Specifically, we make use of the human-constructed tables in Wikipedia. The assumption is that, with respect to the table title, facts that are selected by editors are more salient to the title than those that were not selected, for example, facts mentioned in Wiki info box. Continue the above example, for pointwise model, the facts in the tables such as height and year of completion, are labeled as positive for the title, future tallest buildings. While facts that are in each entity's info box but not in the table, are labeled as negative. When it comes to pairwise model, we simply label facts appearing in the table as more informative than those or not. At the evaluation, we demonstrate that our approaches achieve better performance than state-of-the-art baselines in terms of several IR-based metrics. This is not surprising because the proposed models are expected to learn deeper patterns underlying the training data, while the baselines only exploit shallow correlation statistics. Between the 2 proposed approaches, pairwise slightly outperforms pointwise, mainly because the pointwise approach has a positive-only setup during training, which brings noise. We further conduct user studies for 2 specific applications mentioned at beginning, which are table synthesis and table compression. Both studies show that our models can identify more informative facts than the baselines. Please refer to our paper for more details. Thanks for watching.